Welcome back. Today we are going to finish up our discussion on bonding by talking about intermolecular forces, which means just between two molecules. So we know what interactions happen inside a molecule, but what happens when molecules are around other molecules? These are called intermolecular forces. There's three types of intermolecular forces that we like to discuss. The first one is called dispersion forces, which can sometimes be abbreviated as LDF. Understand that it can be abbreviated as LDF, and what that means is London dispersion forces. London's named after a person, not the city, but London dispersion forces. Now, dispersion forces occur when a particle as its electrons shift from side to side. This creates a temporary dipole, and this has a domino effect affecting everything else. Let's describe this a little bit, just to kind of give you an example of what this looks like. Say, for example, I have chlorine and chlorine, and they have electrons, right? In fact, they have electrons around them like this. Electrons don't just stay in place. They don't just sit in their seats and wait. They kind of shimmy. They move along the molecule like a wave. They kind of pass back and forth. And when they do this, they create dipole moments. Remember that dipole means two different poles. They create brief polar moments. So even though this is a non-polar bond, they kind of shift and shake like a wave. And there might be a moment where this side has a little more electrons than the other side, which creates a very temporary and brief dipole moment, meaning that there are two poles of this molecule. Now, when this happens, and it's next to another chlorine gas molecule, because remember, they're in a container with maybe just millions and millions of molecules. When one does a wave, it affects the other one, right? Because this one now has repulsion forces, and it pushes all of the electrons away from the negative side. So it's almost like as soon as one starts a wave, the other one starts a wave. And now everyone's wiggling and jiggling. And then there are forces connecting these two things. We illustrate those forces oftentimes with dashed lines. It means that there is an attractive force between that partially negative and that partially positive side. This occurs with everything. It doesn't matter if something's polar or non-polar. Everybody's wiggling and everybody's jiggling. And they're all doing this and shifting their electrons around in separate places. This force gets stronger the larger we are, the more electrons we have, and just the larger. So the more electrons you got, the more wiggling and the more jiggling you can do. So that kind of makes sense for this. Again, just as a point of clarification, everything experiences dispersion forces. So if I ever ask you what intermolecular forces are occurring on this molecule, the first thing you always say, dispersion forces, because everything has dispersion forces. But some have more than dispersion forces. Let's talk about those. Our next force is called dipole-dipole forces. Dipole-dipole forces occur between polar molecules. So before, with dispersion forces, it was between anything, nonpolar or polar. Dipole-dipole is specifically for polar. The term dipole-dipole means that it's a molecule that has both two different types of poles. So it has to be a polar compound. Dipole-dipole is often stronger than dispersion, and it's about 1% as strong as covalent or ionic bonds. So it's not as strong as like a full-on covalent bond, but it is, it's stronger than dispersion. There is a table in your book that kind of illustrates what these bonds do. So really the big takeaway here is that the stronger the force is, the stronger our dipole-dipole force is, the higher the things like melting point, boiling point, and freezing point are for different compounds, which makes sense, right? The harder they hold together as overall molecules, the harder it is for us to separate them through physical means. So what this looks like, say for example, we have hydrogen and chlorine, and this is a polar molecule, right? Hydrogen has a partially positive and chlorine has that partially negative. And while they are polar by themselves, that means we have one side of this molecule that's very negative and one side that's very positive. They're also surrounded by other hydrogens and chlorines. So this is partially positive, this is partially negative. And just like with dispersion, they're somewhat attracted to each other based on that positive and negative force. Now, the bigger the dipole-dipole strength is, the harder it is for you to separate those things because we have bigger negatives and bigger positive charges. Now, kind of on that same vein, we have this new concept called hydrogen bonding, which is a type of dipole-dipole force. So understand that you can't have dipole-dipole and hydrogen bonding at the same time. That doesn't really make sense because they are the same. They are both hydrogen bonding. Now, or excuse me, they're both dipole-dipole. But hydrogen bonding is a special type of dipole-dipole. It's almost like superpolar, right? We're talking about super differences in our electronegativity. This only occurs between molecules that have an N, an O, or an F bonded with hydrogen. This doesn't say this in your notes, but please change it to make sure that you understand that they have to be bonded with hydrogen. That's what makes it a hydrogen bond. This is approximately 5 to 10% as strong as a normal covalent bond. It is stronger than a dipole-dipole bond because of this large difference in electronegativity between N, O, or F and hydrogen, or between the small sizes of these different molecules, N, O, F, and H. So between hydrogen, and N, O, or F. So the way that this is going to work is, say, for example, we're dealing with hydrogen and fluorine, and I'm going to illustrate this a little differently. Excuse me, my noggin's in the way. This time I'm going to show this really big symbol to show that we're talking about super big differences in electronegativity, and it's the same thing as dipole-dipole, where one positive side is attracted to another positive side, and we get this strong connective force between those two, stronger than a usual dipole-dipole. So again, this is the same as dipole-dipole, but it's like a super version of dipole-dipole. We could not have the same at the same time, either one or the other. So here's a good summary of intermolecular forces. A molecule that is nonpolar will only exhibit dispersion forces. A molecule that is polar will exhibit dispersion forces and dipole-dipole forces or hydrogen bonding, meaning one or the other. It could do either one. Okay? For examples, let's look at our Lewis structures. So I'm going to write that right here, and then I'm going to go over there. Take a second and flip back in your notes to your Lewis structures, and we'll kind of run through them, so we'll talk about polarity. Here we are back at our Lewis structures. So this is, again, back in the notes. We've already been here. Let's think about the type of intermolecular forces that are occurring. We'll just pick a couple of them. We won't have to do all of them. Say, for example, we're looking at CCl4. In order for us to determine what intermolecular forces are applying to this particular thing, we would first have to think about its polarity. And then as soon as we know what its polarity is, we know what intermolecular forces are occurring. So, for example, looking at CCl4, this is a symmetrical molecule. So this is nonpolar, which means the only intermolecular force is dispersion. Say we're looking at NF3. This is a polar molecule based on its symmetry. We have that lone pair, which makes it polar. Since it's polar, that means it is dispersion, and it has to be either dipole-dipole or hydrogen bonding. So you have to ask yourself, is there a hydrogen bond? And if so, is it bonded to one of hydrogen's special friends? Nitrogen, oxygen, or fluorine? No, so this is dipole-dipole. That's it. Looking at this one, polar again, because selenium has the lone pairs. Is it hydrogen bonding? No, so this is dispersion and dipole-dipole. Again, nonpolar, just dispersion. Nonpolar, just dispersion. Nonpolar, just dispersion. Nonpolar, you might think, well, this doesn't look very symmetrical, but remember, as long as everything on the ends are the same and there's no lone pair, it is symmetrical, which makes it nonpolar. That's it, just dispersion. Let's try and find one that fulfills a different criteria. Let's see. Let's say, for example, we look at just something real quick. Let's just look at NH3. So in this situation, we have NH3, which looks like this. Just like that. And if I wanted to determine whether this is polar or nonpolar, I would say it's polar based on the lone pairs. And I would also say that this is dispersion, because dispersion is always true. And it's also hydrogen bonding, because now I have hydrogen bound with one of its special friends. I wouldn't say it's dipole-dipole and hydrogen bonding. I would just say it's hydrogen bonding.